So for the rest of the session now, we have 3 papers. So for each of the papers, we'll have 25 minutes for presentation and 5 minutes for question, although it's a little bit back and forth. And so what I'd like to do is invite our first speaker, who is Ricardo Lent, who's going to be presenting paper Evaluating a Cognitive Extension for LTP in a Spacecraft Emulation Testbed.
Thank you. Yes, perfect. Thank you. So, can you hear me? Yes. So, yeah, this paper is somehow related to the paper that Fred and Rachel presented this morning. It started possibly a few years ago when I was starting looking at this problem of DTN, and I was studying how to use ion. And I stumbled at configuring the segment size, right, which is one parameter in ion. And I was wondering how to select that parameter. So it's a value that should it be large, should it be small? So pretty much this is the starting point of this work. I'm glad that there were presenters already talking about LTP, so I don't have to cover much or just go straight to the point, which is this work investigates a data-driven approach to basically maximize the reliable performance of LTP by setting this particular value, right, which is the segment payload size. So just to motivate a little bit more, why is that I will be interested in varying that value over time. I'm going to show you first how it is done right now today. This is taken from the ion pretty much example configuration, which comes with the ion distribution. And one of the parameters, which is this one, determines the maximum segment size, right? So in this case, we'll set to, I think it's this one, it's 1024 in this case. And this is done, of course, before we can start sending any bundle. This is something that someone has to decide, someone with sufficient expertise and knowledge of what is going to be the operational conditions of the channel in the future. Which HCTN is very similar. There is a parameter which is the LT data segment MTU, which pretty much does the same, right? So when we start the software, the CLA basically reads this parameter and configures the object to use that particular size for entire pretty much duration of the lifetime, let us say, of the HCTN process that is handling the LTP communication. A little bit more about how this process is done, just to perhaps have some background before we can start explaining how is that we set up this value. So this is the way, it's very simplified description of how reliable LTP operates. Essentially established, the sender and receiver establish a session, and then for every bundle or block that needs to be sent, the sending engine divides this piece of information into a number of segments based on that parameter, right, that we discussed before. And so as a result, I'm going to have, a certain number of segments that I'm going to be transmitting. Some of them may get to the destination, some others may not, right, because of different channel impairments. And as a result, LTP, when we request LTP to send reliably blocks or bundles, we'll try to retransmit whatever was lost during the transmission cycle. And for this, it basically implements an acknowledgement mechanisms that tells the sender what was received, so it can send whatever was not received during a second attempt. Nothing, of course, guarantees that everything will get through during the second attempt, so we may get back another acknowledgement saying that something was not received, so we will have to send again, and so on. So this process will continue, of course, many times until the whole block gets to the other end. And as a result, we're going to have reliably transmitted, a block to the receiver, right? But in situations where we have very long delays, this process will, of course, impact performance, given that each retransmission time will imply at least an RTT time. So that could be very costly for very long transmissions. So there are some additional, of course, mechanisms which are not that relevant to this discussion, but of course are implemented in LTP. So coming back to the original problem, we can start by looking at the problem from a very, fundamental perspective, just, coming back to perhaps networking 101, right? Where we study the efficiency of protocols, right? So the efficiency of any protocol is essentially the ratio of the data that we want to transmit over the total amount of data that we have to send, including any control information. So in the form of headers or whatever else we have to transmit. So in the case of retransmissions, of course, it's not really useful data. In a sense, it's going to be some sort of overhead, right? That we're going to have to retransmit. But let's have a look first at the nominal case, the case when we have no losses in the channel. So the only thing driving efficiency in this case will be the header, right? So the header overhead will be what will be giving us lower or higher efficiency. So this is the expression after a little bit of algebraic manipulation, right? But this is essentially the efficiency that we get is 1 minus. Basically, that's the bundle overhead, the bundle header overhead, or blocks as it is known for bundles, divided by the total size of the bundle. And on the denominator, we have 1 plus the ratio of the LTP header size, including any underlying protocol overhead, divided by the payload that we want to transmit, right? So the payload is over there. So that's the parameter we can select if we want, and that is going to determine what is going to be the efficiency of our protocol. Now, this is for the ideal case where we have no losses in the channel. What will happen if we do have losses? Okay, so in that case, we have to consider what will be the bit error rate of the channel, which essentially we can treat as a probability, right? Probability of having a bit clip when transmitting data. If we assume, and this is where a very generic assumption, if we assume that the errors are distributed identically, independently, and after any forward error correction code, we still have this bit error rate B, what will be the probability of losing segment, right? So that will be determined by how long the segment is, right? So we're going to have the expression over there, 1 minus B, and this is to the power of the, basically the segment size, which includes the header and the payload. And of course, if we have a very large payload, the probability of error is going to go up. So as a result, you see, we're going to have to deal with this trade-off. If we have very large segments, as was discussed this morning, we're going to get a lot of very high efficiency only if we have a very reliable channel, right? But if the channel is not reliable, then we're going to have to pay the price of having to retransmit. So there is a trade-off there that we have to play with. Okay, so we can have a look at the average number of segments that I will have to transmit to reliably deliver a block that is given by the summation over there. That's a very simple expression, just a geometric summation, right? And that gives us, on average, n divided by 1 minus p. And we plugging into the efficiency, we do a little bit of mathematical manipulation. We end up with the expression over here, right? Which is very simple. Is basically the efficiency that we had before multiplied by 1 minus p. Okay, enough of equations. Let's have a look at charts. Yes, so what we have over there is a chart of the efficiency, protocol efficiency. The blue line is the nominal efficiency with no channel with no errors. What we have on the x-axis is the payload size, right? So what we have here is that if we have no errors in the channel, it's best to use the largest possible segment size, right? Which is exactly what Fred was discussing this morning. However, if we have a situation where the channel starts experiencing errors, the bit error rate, is gonna drop the efficiency down. But what is interesting is that we're gonna start observing these peaks. Yes, so the peaks are the points where we want to be at. We want to operate on these peaks. And you see that peak moves depending on the bit error rate, and also depends on the payload size that we choose, right? So in the end, we want to maximize, of course, efficiency, which is, conversation problem. Because I have this equation, it's very easy to get the maximum that we just need to derive make it equal to 0. And then we get the expression over here, right? So let's have a look at additional charts. So what we see over there is the optimal payload size as a function of the bit error rate. And this is pretty much in line with what Fred presented this morning, right? So we want to have very, very large, super large bundles if we have a very reliable channel, right? But as the errors start kicking in, we want to reduce that in order to keep the efficiency high, right? So this is the envelope, essentially, where we want to be operating. Okay, so this is very nice. This is theoretical result. Does it apply in practice? It's the big question, because I'm assuming, of course, that we have identical independent distributed errors, which may not hold in practice. We also need to know what is the BER of the system, which we may not know in practice either, right? So the proposal then is to develop something that will adaptively modify the segment size depending on certain observations. And for this work, well, we looking at the number of retransmission rounds that LTP requires to deliver a bundle, right? Because somehow that is going to give us a sense of whether the channel is good or not, right? So if that number is large, it's because we have to retransmit a lot. That means we are not doing well. We should reduce the bucket size, right? And the opposite is the same, right? So if we are just requiring one transmission round or maybe two transmission rounds, that means the channel is very good, so it makes sense to use large. Yes, but we don't want to make that decision, of course, manually. We want to have some system that's going to do it for us. And this is the system that we are basically proposing. So we have these blocks entering just a standard LTP engine. We're going to have some decision-making unit that is going to tell us what is the segment size that we should be using. So we use that value to do the segmentation. We send the bundle, the segments. And later on, we're going to receive some feedback about how many rounds we require to send the block. And that we're going to tell the decision unit, which is going to adjust the decision based on that observation. But it's basically reinforcement learning what we have here. I'm not going to give a lot of details on the architecture, but I'll just mention briefly that decision unit is spiking neural network. It's a unit that was developed previously and applied to optimize bundle routing. In a way, we are reusing it here for this problem, because the problem is very similar, right? So in routing, what we do is we select next hops, and what we like to do here is select the next bundle size, or the next segment size, right, to be used. So in a way, it's a related problem. So I want to give a lot of details, but the idea is that these neurons communicate in the form of spikes, and the dynamics of the system are pretty much described as an electrical system by the equations that you see there. And well, the solution of the equations will tell us basically the spike emitting behavior of these different neurons. And based on that behavior, we associate with a decision on which segment size to use, right? So there are some additional equations that I will skip just in the interest of keeping the presentation short, but I'll be happy to, discuss later if you have any question about those. So let's move to the implementation. In order to test the idea, we try to implement it for HTTPN. So in HTTPN, there was already yesterday a presentation by Brian. So again, I don't have to give you a lot of details here. But essentially, we use just the standard LTP over UDP that is in HTTPN. And I put here the main classes that had to be modified, because there is no immediate way right now of externally telling HTTPN to use this new segment payload size, right? So we can tell at the beginning, but later on, it's not possible to update So we have to do some modifications to the existing code. In reality, if HCTL could allow us to tell dynamically what is the segment size to be used, and it could tell us some performance indication in the form of how many rounds we need to transmit a bundle, then this won't be needed, right? So we could do everything externally to LTP without any modification to the base code and protocol. Okay, so these are the things that we modified. Essentially, we introduced MPU client server data, which I think is already there, but that's the variable that is initialized at the beginning. That's something we dynamically change in the code. We also defined the number of actions that we want to consider. Number of actions basically implies the number of different segment sizes that we have available, yes, to make a decision. And then we have a vector with the actual value, right? So this is something we have pre-designed. So in the experiments, for instance, we use, if I'm not mistaken, 100, 200, 300, something like that, right? So these are the possible segment sizes that we could use. And then the LTP session sender was also modified, well, to have this number of rounds variable that we keep updating. And the variable is updated after the code executes certain callbacks, right? So what is good about HTTL is that it's got a lot of callbacks that we can use to, in a way, customize the behavior of the protocol. So we have, for instance, a callback that is invoked when we receive a report, right? Or whenever we have an expiration, a timer expiration, or when we receive a segment, report segment, so on, right? So based on those callbacks, we update this parameter over here. And that is essentially the one we use to train the neural network. Now, in addition, we also modify this LTP UDP engine manager, which is the one in charge of first receiving segments. And here we introduce this notion of having a target bit error rate. This is just for testing purposes, just to make the engine drop certain packets, right? For testing purposes. So that was introduced into this function handle UDP receiver. Right. But this is only used if we want to, run some tests where we want to have a specific drop rate for the bundle, for the segments. Okay, some results. We ran two sets of experiments. The first set was run on a lab test bed. The reason for having two tests was, number one, that it was easier to develop the code, using just a networking test bed rather than having actual radios. Number two, it was also easier to run the experiments for longer time using a networking test bed. So, okay. So the networking test set is very simple. It consists of just two PCs connected with a UDP cable. And here the delays, of course, the delay is emulated using NetM. And the bit error rate is emulated as well by using the implementation that I mentioned earlier, right? So we drop certain packets depending on their size. We drop packets with a given target bit error rate. So here we do have report for four different bit error rates. So what we see is in blue, we see the results that were obtained by fixing the segment sizes to whatever value is given on the x-axis, right? So what we see here is a bit error rate of 10 to the minus 6 implies a very good channel in general. And we see that by using larger segments, we achieve a lower delivery delay. Yes, and that is more or less the expectation because overhead, is something that needs to be transmitted, consumes bandwidth, and so on. So in this case, it makes sense to use a larger segment than a smaller segment. So what you see here are the results obtained with this adaptive method. Again, this is delivery time, right? So you see that the delay that we obtain more or less corresponds to the lowest delay that we observe, right? By fixing the segment size. So on average, the mean was 960. I forgot to mention that because we use, UTP cable, the maximum possible segment size will be 1500, right? Because it's 300. So we cannot go beyond the particular level. Okay, so as conditions get worse, and we get to the opposite end over here, we see that we get better results, by creating a smaller segment, right? And that is again what we discovered, right, dynamically by using this adaptive method. So in between, we got some sort of mixed result, but still within the expectations. So you see in this case with 10 to the minus 5, if there is no clear winner, it doesn't matter much where we put our bet. Yes, and our method will basically discover a length of 800, and in this case 700, right? But there's no clear winner right here in this relative. Okay. Now moving to the cognitive ground test bed. I think something happened with my slides, so I'm just gonna keep the slide with the results. But this is a system that Rachel presented before, and basically consists of SDR radios, and there is a channel propagation emulator, which provides reasonable realism in terms of the signal transmission. In this case, of course, we didn't require to introduce any emulated segment drop. What happened here is that the packets will be dropped naturally because of errors in the channel, errors produced by the radio transmission in the channel. So what we see here are results for the interference-free scenario. And we observe that the segment size, right, that our method discovered was around 1,000. And for this scenario, for the radios, there was a limitation on the MTU. The MTU was 1005, I believe, 1005 bytes, right? So the method actually discovered that that was the best, right? That maximum value was the best to be used. And again, we see, that is correlated to the results of the delivery time, right, which match the manual setting of the segment size, at the lowest delay, also at the lowest bundle loss ratio. Yes. Now to test noise conditions, we introduced a second signal. Was a QTSK signal at 1.65 gigahertz, this particular power level. And in this case, we observed the following behavior. The protocol was able to discover, an optimal segment size of 460 bytes, which more or less, again, corresponds to the minimum loss, depending, compared to manually fixing the values, and the same for the delivery time. Okay, so to conclude this work, where it's just an exploration, of how to set dynamically the payload size in LTP, it could be extended to cover all the parameters, of course, right? So as Rachel mentioned in the morning, there are a lot of parameters that needs to be optimized. So it's data-driven, and again, it's only one possibility, right? It doesn't need to be neural networks. It could be something else. But that's, well, the method we explored in this work. And we validated the result experimentally, which is essentially a step forward. The previous result that we had, which were essentially theoretical and simulation. So we observed the expected adaptation. We did encounter some additional considerations, right, that were not in the model. One of them was this MTU restriction, so which doesn't allow us to grow larger than a certain amount. The other problem was related to radio synchronization issues. So the thing was that by introducing too much noise, the radios pretty much lost synchronization, and they started losing bundles. And that didn't give us, any chance of making any modification because they were lost anyway. So that's a complication that is, outside, not visible by the models, but it's something that is encountered in practice. Well, that's pretty much what my presentation is. Thank you very much.
Do you have any questions?
Hello, thanks for the presentation. Very, very interesting. My question is on, did you configure any specific time hysteresis between segment size changes?
Time?
Yeah, so basically how frequent would the segment size change?
Okay. We complete one block transmission, and then the next block gets a new segment size. It's block per block, yeah. It's sequential.
Yeah, thank you, Carlos, for the nice talk. I was wondering, how are you training the model? I think I missed that. Is that online?
No, I didn't cover because I wanted to save some time.
Okay,
It's exactly the same method I'm using in routing. Essentially, it's reinforcement learning. So we do the thing. So we give a segment size. We do the blocking, the segmentation we transmit. We receive back how many sessions, so how many rounds we needed to transmit reliably the block. And that we use as a cost to modify the weights of the derivative.
Okay, so it's an offline simulation.
No, this is online. This is happening online. So you get the feedback, modify. So the next block gets the updated information.
Okay.
So it's doing it all the time.
My follow-up question about that is then, you propose some theoretical, like mathematical modeling.
Yeah, because
can't we estimate the optimal sweet spot analytically?
We know what is the optimal sweet spot, but we don't know what is the bit error rate. I mean, we don't know what the parameters are.
But I mean, you can measure the bit error rate, right?
At the receiver, but we are at the same.
So, but if the receiver does feedback, the bit error rate, then
it could be a way. Yes, it could.
I can get the theoretical optimum instead of a machine learning training.
It could be right.
Okay.
I mean, that could be another way. Yes.
Okay.
But that will need to send back.
It's CTN and so on. So
I'm reusing what exists because LTP already sends back acknowledgements, and I can just count how many transmission rounds I needed. Right? Mm-hmm. So that's what I'm using. But I could use something else. I could use the actual bit error rate or something or time. Yeah.
Regarding the last challenge that you mentioned with the limitation.
Yes.
In the previous talk, they were talking about when the MPUs restricted, you have to go with fragmentation.
Right.
But you run trip is something at the segment level.
Right. So I'm not considering any fragmentation here. So I'm looking at what is the maximum MPU of all the underlying layers, and then I'm selecting my options based on that maximum. Right, so 100, 200, up to that maximum. Yes.
So if the fragmentation happens,
yep, that's a very interesting. That will be a very interesting addition. That will change also the theoretical analysis, which is something I will be very interested in doing, but I haven't done it yet. Yeah, but it will change. It will change things. It will change things quite a bit.
Somehow.
It will. It's something you configure at the beginning, right? So it's something you manually set as a parameter here. So you need to know, you can check, right? What is your underlying protocol's MPU, and then accordingly you can set that value. Do we have time?
Yes, one more. Yeah, I was just wondering, when you use the radio, how much was this value changing? Is it jumping along, following this metric, the segment size?
We're using the radio. Well, we do sequentially. We transmit the whole block,
Effective part. How much was this like? Was it
every time we get back, every time we finish transmitting one block, we get the reward signal or cost signal. Then we update the neural network. So the next block will get this new value.
And was this changing a lot?
Well, it depends on how fast you send your blocks, right? I was sending at, I think, 300. I don't remember right now. Oh, 2 bundles per second. Sorry, 2 bundles per second. So it will depend on how fast you send your blocks.
For one more, please.
Yeah, I was just wondering what use case is LTP over UDP in the context of radios? That's not the way we do it in space.
Well, I just use the standard because LTP over UDP is let's say, the default CLA for
If you're on
LTP.
terrestrial internet, LTP over UDP is true. If you're in a space condition, it's LTP segments over AOS or TM or TC.
That's right.
Techniques. It'd be interesting to see your techniques.
Right, it will be, I think so, yes. It will be interesting to repeat using a
training
different.
style is fixed by the coding standard you're using. So you don't get to change.
And in that case, we won't be able to do any optimization.
Put multiple frames multiple segments into a frame. And so there's an awful lot of optimization you could be looking at.
Right, but it will be a different kind of optimization, most likely, right?
Actually, we do have one more. One, do you have a question?
No, I'm done. Thanks. Yeah.